In this video, I would like to talk about model predictive control for a class of discrete-time nonlinear implicit systems. First, I would like to introduce the system model. X and U denote the system state and control input, respectively. Then, discrete-time nonlinear implicit systems are described by this equation. In this system model, E is a constant matrix and F is a differentiable function. When E is the identity matrix, the system is called the explicit system, that means the usual nonlinear system. When E is singular, the system is called the descriptor system. For this kind of nonlinear implicit systems, H-infinity control method has been already established. However, for generalized nonlinear implicit systems as shown here, no control methods have been proposed. That means, in the case where E is the state-dependent matrix-valued function, a control method has not yet been proposed. Therefore, in this study, we focus on this class of nonlinear implicit systems. This is our motivation in this research. So, the objective of this study is to propose a control method for this class of nonlinear implicit systems. Especially, I would like to propose model predictive control method for this system. Model predictive control is a kind of optimal feedback control, and its performance index has a moving initial time and terminal time. The current control input is obtained by solving a finite horizon open-loop optimal control problem using the current state of the system as the initial state, and this procedure is repeated at each sampling instant. Model predictive control is a form of control in which the current control action is obtained by solving a finite horizon open-loop optimal control problem, at each sampling time, using the current state of the system as the initial state. The optimization yields an optimal control sequence, and the first control in this sequence is applied to the system. Thus, this procedure is repeated at each sampling time. To solve the model predictive control problem, we must derive the stationary conditions, also called the Euler-Lagrange equations. This is because the stationary conditions must be satisfied for a performance index to be minimized. For explicit systems, the stationary conditions have been already derived. However, for implicit systems, the stationary conditions have not yet been derived. Hence, to derive the stationary conditions for implicit systems is a significant work. This is the outline of this talk. I have already explained the research background and the objective of this study. Next, I would like to talk about generalized Euler-Lagrange equations. The control input is determined so as to minimize this performance index introduced in a general setting. Phi is the terminal cost function, and L is the stage cost function. The minimization problem of performance index J subject to the system equation can be reduced to the minimization of the following performance index introduced using the Lagrange multiplier. Here, lambda is the Lagrange multiplier associated with the system equation. Now, the optimization problem subject to the constraint has been reduced to the minimization problem of J bar without constraint. Then, for notational simplicity, we introduce the Hamiltonian H defined like this. Let delta denote the variation, that means the infinitesimal change. We need to consider the variation in J bar due to the variations in x, lambda, and u as shown here. Applying the Taylor expansion into this term and neglecting the high-order terms of each variation, we can compute the variation in J bar. Then, based on the variational principle, the so-called stationary conditions can be derived so as to satisfy this condition at the red underline for any variations in x, lambda, and u. So, we can obtain the stationary conditions that must be satisfied for the performance index to be minimized. Let the obtained stationary conditions be called the generalized Euler-Lagrange equations. This slide shows the obtained stationary conditions. These conditions from k equal t to k equal t plus n-1 must be satisfied for the performance index J to be minimized subject to the system equation. Note that, when E equal to the identity matrix, the obtained stationary conditions are reduced to the well-known Euler-Lagrange equations. So, these conditions are natural extensions to the well-known Euler-Lagrange equations. Generally speaking, Euler-Lagrange equations cannot be solved analytically for nonlinear systems. So far, several numerical solution methods have been proposed. Next, I would like to briefly explain how to numerically solve the obtained generalized Euler-Lagrange equations. In fact, the stationary conditions are classified into four parts: equation of the state x, and the terminal condition, and the equation of lambda, and the optimality condition. Note that the stationary conditions are classified into the equation of x, the terminal condition, the equation of lambda, and the optimality condition. Let capital U be defined like this. That means the sequence of control inputs over the prediction horizon. This figure shows the procedure for numerical solution. For given optimal solution candidate UT in the current state xt, we first compute the x-form k equal t, to k equal t plus n, using the condition enclosed by blue line. Next, the lambda at the terminal time is determined from the state at the terminal time using the terminal condition enclosed green line. Then, lambda is calculated from k equal t plus n, to k equal t, using the condition enclosed by red line. For obtained x, lambda, u over the prediction horizon, the optimality conditions enclosed by yellow line are not necessarily satisfied. We need to suitable update u so as to decrease the norm of d. The norm of d is used to evaluate the optimality performance. Several algorithms have been developed such that the norm of d can be decreased by suitably updating u. For example, CGM, less method and contraction mapping method are useful for suitable updating u. Detailed information about these methods can be found in these papers. Next, I would like to talk about the stability of the nonlinear implicit systems with model predictive control. For usual explicit systems, the stability criterion of the closed-loop system with model predictive control has been established as shown here. If there exists the control input satisfying this inequality, then the stability of the closed-loop system with model predictive control can be guaranteed. Note that there is a restriction on choice of performance index to guarantee the stability of the closed-loop systems with model predictive control. So, we can see that if the terminal cost function plays a role as a control Lyapunov function satisfying this inequality, then the stability of the closed-loop systems can be guaranteed. In this study, we establish the same stability criterion for implicit systems with model predictive control as shown here. Under several assumptions, if there exists the control input satisfying this condition, then the stability of the closed-loop implicit systems with model predictive control can be guaranteed. The proof can be found in this paper published in IEEE CDC. Next, I would like to talk about an illustrative example. Here, we consider RLC network system described by Brayton-Moser equation as shown here. X1 is the inductor current, X2 is the capacitor voltage, U is the controlled voltage input. Then, we choose a performance index as shown here. In this simulation, we apply the contraction mapping method for numerical solution. Left figures show the free responses of x and the norm of x without control input. We see that the state doesn't converge to zero. On the other hand, right figures show the time responses of x and the norm of x with control input. We see that the state converges to zero. Left figure shows the time response of control input. Right figure shows the time response of optimality error evaluated by the norm of d. So, the effectiveness of the proposed method was verified by numerical simulations. Finally, let me summarize my talk. In this study, model predictive control method was proposed for a generalized class of nonlinear implicit systems and then generalized Euler-Lagrange equations were derived. In this talk, numerical solution method for solving the generalized Euler-Lagrange equations was briefly reviewed. Furthermore, the stability criterion for the closed-loop nonlinear implicit systems with model predictive control was shown. Finally, an illustrative example was provided to verify the effectiveness of the proposed method. That's it. Thank you for your attention.